Welcome friends to my YouTube channel Sommo Physics. Now yesterday I told about the changes in entropy for a reversible and irreversible process. Okay. Now in today's lecture I shall going to discuss few other issues related to entropy. First one is that I told that entropy is a measure of unavailable energy of a system, and now I am going to explain it more accurately by taking a suitable example. Okay, so let us consider the example of heat conduction through a rod. Okay, heat conduction through a rod. Okay, now suppose there is a rod and temperature at the one end is T1 and the another end is T2. So if T1 greater than T2, then heat will flow from this region to this region. Okay. If temperature T1 is greater than T2, then heat will flow from this region. Okay. Suppose Q amount of heat flows from a region of temperature T1 to a region of temperature T2, and say T0 is the lowest temperature, which is available to us, which is available to us. Okay, so at first when heat conduction takes place, that means heat moves from here to there, then what we can write, then what should be the amount of energy required when heat conduction occurs. Okay, so when conduction takes place, then the amount of energy, say E1, what is that? Say when heat conduction takes place, then Q amount of heat will be available at this position. Okay, so we can write the available energy, say this is W1. Okay, say this is W1. So what should be this? This is Q multiplied by 1 minus our lowest temperature is T0, and now when conduction takes place, then Q heat will be available to a temperature T2. So this. Okay. So when heat conduction takes place, we can write the amount of energy or work required, which is this Q into 1 minus T0 upon T2. But when heat conduction does not take place, then Q amount of heat is available at this region. Okay, because conduction had not occurred. So when conduction does not take place, then what will be the amount of energy? You can write it, say W2, this equals to Q into 1 minus T0 is the lowest temperature, and this time Q heat will be available at temperature T1. Okay, so this is the case. So if you subtract this, okay, so here T1 is large, that means this term is small, so this W2 is large. Here T2 is small, that means this becomes large. Okay, so here W2 term is greater than W1. Since T1 greater than T2, this term will be greater than this term. So if you subtract this from this, you will get the amount of energy unavailable for work. Okay, because the first part is when heat conduction takes place, that means there will be a energy loss, and the second case when heat conduction no heat conduction, that means no energy loss. So if you subtract this, you will get the unavailable energy. Okay, this is the total energy and this is the energy required. So if you subtract these two, you will get the amount of unavailable energy. Okay, So what will be the amount of unavailable energy that we have to find out. Okay, so amount of energy that is unavailable for work, that is unavailable for work. If you say call it delta E, then it would be simply W2 minus W1. So what will be my W2? Q into 1 minus T0 upon T1, and this simply 1 minus T0 upon T2. Okay, so 1 cancels, so what we get? T0 upon T2 minus T0 upon T1. So if you take T0 common and Q you take inside, then what would we get? T0 into Q by T2 minus Q by T1. Okay, so this is simply S2 and this is simply S1. So you can write T0 delta S. So thus we can see that the amount of energy which is unavailable for work is T0 times the increase in entropy of the universe. Okay, so it has a significance, I tell it. Okay, so what is the significance of it? So we explain the unavailable energy by taking a suitable and simple example of heat conduction. Okay, so we see that the amount of energy unavailable for work is T0 times the increase in entropy of the universe. Now, if you look into this equation, then we already told that all in natural processes that occurring in nature are irreversible. So the entropy of the universe is increasing. That means this term increasing, which as a result delta E increases. That means unavailable energy increases. So what is it? Amount of unavailable energy increases means there will be a less amount of energy which is converted to work. Okay, there will be less amount of work, that is less amount of energy will be converted to work. Okay, so entropy of the universe is increasing, as a result unavailable energy increases. That means available energy decreases. Okay, so unavailable energy increases because delta S is increasing. Okay, so that means available energy decreases. So available energy decreases. Available energy decreases. So this is known as the law of degradation of energy. That means available amount of energy which is required for the to convert into work decreases. So available energy decreases means this is called the law of degradation of energy. This is called law of degradation of energy. That means available energy is decreasing. That's why it is called law of degradation of energy. Okay, so this is one thing that I tell. Okay, so entropy is a measure of unavailable energy of a system. Okay, so this is the concept of unavailable energy and the law of degradation of energy by taking a suitable example of heat conduction. Okay, now we are going to discuss an important theorem which is known as Carnot theorem. We use this theorem in our previous lecture in case of change in entropy for irreversible process. So let us take Carnot theorem. So there are two parts of Carnot theorem. Today we will prove the first portion, Carnot theorem. Okay, so the first part of Carnot theorem is that efficiency of all reversible heat engines working between same two temperature limits are same. Okay, that means if you consider 5 reversible engines working between same two temperature limits, then their efficiency will be same. So how we can check it? By using the concept of entropy. Remind it, by using the concept of entropy. Suppose a reversible engine works between two temperatures T1 and T2. That is at T1 temperature it absorbs heat from source, and at T2 temperature it rejects it to sink. Okay, so the engine absorbs heat from source. That means the entropy of the source is decreasing. Okay, the entropy of source is decreasing. So if Q1 is the heat absorbed from source, then what will, since the engine is extracting heat from source, the entropy of the source is decreasing because heat is extracted from this. So decrease in entropy of source, decrease in entropy of source. So what will be, that is Q1 upon T1. Now the engine rejects Q2 heat to sink, so heat is given to sink. That means its entropy increases. So increase in entropy of sink, what will be? The increase in entropy of sink, this is what? Q2 upon T2. Okay, so what will be the net increase in entropy? My net increase in entropy will be this, Q2 by T2 minus Q1 by T1. Okay, and since the engine is reversible, we know for a reversible cycle the change in entropy is 0. That means this net change is 0. We can write, so from which we can easily write Q2 upon T2 equals to Q1 upon T1. Give it a name, say ds. Okay, ds. Since the cycle is reversible, the change in entropy is 0. Okay, since the cycle is reversible, the change in entropy is 0. Okay, so what will be my Q2? My Q2 will be T2 ds and my Q1 will be T1 ds from this. So what will be the efficiency of the engine? So let us check what will be. Is it agrees with the Carnot cycle or not? So if we call the efficiency of the engine is eta, so my result will be, general formula is 1 minus Q2 by Q1. So substitute it. Q2 means T2 ds and Q1 means T1 ds. So ds cancels. So this. So we see that this agrees excellently with the efficiency of the Carnot engine. So we can easily conclude that efficiency of all reversible heat engines working between the same two temperature limits are same. Okay, so efficiency of all reversible engines working between same two temperature limits. Okay, efficiency of all reversible engines working between same two temperature limits are same and is equal to the efficiency of a reversible Carnot engine. So this proves the first part of the theorem, that is efficiency of all reversible engines have the same efficiency that is working between same two temperature limits. Now in our next class I shall discuss the second part of Carnot theorem, which is no engine is more efficient than a reversible engine, that we discuss in our next class. So dear guys, if you like this video, then kindly subscribe my channel and share it to your friends to get latest updated videos on higher secondary and graduation physics. Okay, thank you.